Great. Welcome. Today we're very pleased. Oh, sorry. Good point. Yeah. Today we're very pleased to welcome Henric Krawcynski. Henric is the Wayman Crowe Professor of Physics at Washington University in St. Louis and is chair of the Physics Department. He got his PhD in 1997 from Hamburg University and did postdocs at the Max Planck Institute for Nuclear Physics, Kernphysik, in Heidelberg and at Yale before moving to Washington University. Henric is both a theorist and an instrumentalist. He does theoretical modeling of radiation in all kinds of high-energy systems, including black holes, blazars, and magnetars, and especially over the past few years has been interested in polarization at high energies. He also does works on instrumentation for X-ray polarization. He is the PI of the XL Caliber mission, which is a balloon-borne mission, which is high-energy X-ray polarization, which has actually been operating for about a decade. And he is also part of the science team for IXPE, which was launched a few months ago. And today he is going to give us the first results from measuring the polarization of X-rays from stellar mass black holes in X-ray binaries. So,
Hey. Well, thank you very much for the invitation. It's awesome to be here. It's incredibly nice, the surroundings, and incredibly stimulating, the intellectual atmosphere. So I want to talk about the Imaging X-ray Polarimetry Explorer. That's like a SMEX mission that was launched on December 9th last year, 2021. And just now it's producing a lot of results, some of which are still embargoed, some of which are already kind of available. But overall, I think we submitted 2 Science and 3 Nature papers, and I think 3 of them are already accepted. So this one, for example, will be published on November 3rd. And is embargoed until then, but we can still give these talks. So well, briefly, like in my briefly comment of what we do at Washington University, then introduce this new mission and show you the results from Cygnus X1 observations. That's like a stellar mass black hole, 21 solar masses with a 40 solar mass companion. And a bit show you a couple of other results. Just for WashU, so we have a physics department, 33 professors. We do 80 graduate students. We do astrophysics, biophysics, condensed matter, nuclear physics, and quantum information. And for this quantum information, just wanted to, if you do any quantum physics, please apply to our positions. We got like a cluster search for 4 or 5 positions because we have a new dean, and one of the main signature initiatives is to sponsor quantum, a center for quantum leaps. So that's still open until November 14. Please apply for that one. Wanted to briefly mention, we do a lot of experimental astrophysics at WashU. So one experiment is, was a balloon-bound experiment, is now on the International Space Station. So it will be there in 4 years and measures the abundance of heavy cosmic rays with atomic numbers larger than 30. One is a balloon-bound mission does gamma ray astronomy. So that will have a flight in 2 years or so and can measure the polarization or the fluxes from gamma ray bursts. Then we have, a bit slow here. Don't know why this is leaving me here. Let's see. Okay, we have one experiment that measures the optical depth to reionization. Johanna Nagy, my colleague, is doing that. And I have this XL Caliber experiment. It's a balloon-borne X-ray polarimeter working from 15 to 60 keV. We just flew it on a 7-day balloon flight from Sweden to Canada. Unfortunately, there was some mishap with accidental ballast drop, so we didn't get much data. And we hope we can fly again in 2023. We did get good data, but also only a day, 3 years ago from launching this from McMurdo. And we observed the neutron star GX301-2 and had some limits on polarization. This can measure 2% polarization fractions in the 15 to 30 keV energy range. So what I'm talking about today is at lower energies, and it's a satellite-borne experiment. Just briefly wanted to mention we have quite a astrophysics theory group now too, with Jai Chuan and Alex Chen doing magnetohydrodynamics and particle and cell simulations. And we have observers, maybe Noah Wando, Novak, and cosmology, and some extrasolar planet.
Mike Novak is a postdoc.
Okay, very good. Right, okay. Let's see if this works. Okay, I have right now have 7 graduate students. They work like 60% of the time on experiment and 40% of the time on theoretical modeling. And then, it's very slow. We have a technical personnel, 2 engineers, and a mechanical and electrical technician. So they help with making these experiments, the balloon bond experiments. One of our activities was to write a new X-ray fitting code. So we simulated 70,000 configurations of accretion disks, like thin accretion disks with some hot gas, and do then general relativistic ray tracing and comptonization of these rays in these coronae, and then predict what the observations are. And we can use that to fit like actual data. So it's kind of different from what is done here, where you do more very detailed physics simulation. This is just kind of toy models, but they kind of cover a large parameter space and can try to describe actual data and kind of get some clues of where, for example, hot gas close to black holes is located. One more activity, show you here. This is like a simulation that we ray trace general relativistic magnetohydrodynamic simulations from Matthew Liska, who is also coming here very frequently. He's a postdoc right now at Harvard, but spends half of the time here. And he simulated a black hole accreting mass where the accretion disk or the black hole spin is misaligned to the outer disk. And then you see that after a while, the inner disk kind of breaks off. And that's kind of owing to the Bardeen-Peterson effect or Lenz-Thirring precession, that the black hole kind of makes the inner accretion disk, aligns it with the black hole spin. And my student Andrew, he kind of simulated the X-rays from these systems, and then analyzed them, and you can see that they see some periodic oscillations which are related to this inner part of the disk tearing off from the outer part and from the inner part oscillating. Before I start with the real contents of my talk, let me show you one. Oh, I also do a lot of experiments. But just wanted to show you, we develop CCT detectors. And this is for a new star follow-up experiment. Maybe no new star measures hard X-rays. And this for these detectors, we develop an ASIC which can get a better spatial resolution, 150 micrometer instead of 600 micrometer in new star. Then we also work together with NIST here in Boulder on this cryogenic detection of X-rays. And these are little absorbers which are kept at like a bit more than a cubic millimeter. And they are kept at 80 millikelvin. And then when an X-ray hits the detector, the temperature changes, and you can measure the temperature change with a transition edge sensor. And that achieves then an energy resolution of 55 eV at 90 keV, while NuStar right now gets something like 2 keV or 1.5 keV. So that's kind of a factor of 20 better than. And we got funded to have a little prototype detector, a little dilution refrigerator this size, and we will put it on a balloon and fly it in fall of 2023 on a test flight. In future, one could have an experiment where this is combined with some crystal optics and then maybe also detect 511 keV gamma rays with these detectors. Okay, so we just wanted to mention and say thank Mitch for this great book and Andrew for the great webpage, because I'm using this a lot. I'm teaching a freshman class on black holes, and these are so the only 15 people can take this class, and then half of the time we do the math, like mathematics of general relativity, and the other half, the students, summarize chapters from Mitch's book, which is a very nice book describing all the phenomenology. And then sometimes we also explore this beautiful webpage and see all kinds of movies about how it is to fly into a black hole. So I wanted to talk about this Imaging X-ray Polarimetry Explorer. So it's a NASA mission, and also like a major contributions comes from the Italian Space Agency. They contributed the detector technology, and it measures like 2 to 8 keV, has some imaging capabilities with an angle resolution of 30 arc seconds, has like 20% energy resolution, and gets the same sensitivity as the previous X-ray polarimetry mission in 1/100th of the time. So the previous mission was called OSO 8 and only had a significant detection of one source, that was a Crab nebula impulsor. This one is now much faster and gets more significant results. And one of them I'll show you today. This was launched December 9. There's an observation plan. All the data become public 1 week after taking them. So if you're interested in analyzing those data, you can just download them from the NASA archive. Briefly show you so I want to talk about this paper. This just submitted in June. It was actually now published. These are the collaborators. It was a big collaboration, and it was really great to, for once, work with all the competition instead of just like writing our own papers, but working together on this paper. So Fabio Molerio, he kind of is our lead analyzer of the IXPE data, and Mikhail Dovchak was the science working group leader, and Alexandra Valedina, she also worked a lot on the interpretation. So we observed Cygnus X1 because it's one of the brightest black holes in the X-ray sky, and it's a galactic black hole with a mass of 21 solar masses, 41 solar mass companion, 5.6 day orbit, and it's at 2.22 or so kiloparsec. We think the orbit inclination is 27.5 degrees, which is kind of important because the more you kind of see things face on, the lower is the polarization owing to symmetry. The more you see it edge on, the higher is the polarization. So we actually had expected to only see 1% or so polarization fractions of this source. And this data will constrain the corona. This is like some hot gas, very hot gas, like temperature of 100 kiloelectron volts, which is somehow created close to the accretion disk. And we don't really know where it is. It could be like the foot of a jet or the base of a jet. It could be kind of like a thing that bubbles up from the accretion disk and is above and below the accretion disk. Or it could be that the inner portion of the accretion flow becomes thermally unstable and somehow puffs up and gets really hot. It's kind of really not working for me. So we're interested in that because it's a diagnostic for how accretion onto black hole works. And you probably know that black holes are responsible for a good fraction of all the light that's produced in the universe. That's mostly supermassive black holes. But for studying these small stellar mass black holes, we kind of can learn how accretion works. It's a prerequisite for interpreting the X-ray energy spectra from black holes. And maybe you know that in these energy spectra, you often see iron K alpha lines. And if you get them from very close to black hole, then you kind of can measure the local clock speed and kind of get information about the space-time. And this works better if you know where the corona is and how it illuminates the plasma, which then emits iron K alpha lines. And then some of these results that we get from stellar mass black holes, they may carry over to supermassive black holes. And then if you, for example, manage to validate or refine some measurements of the black hole spin, then this would have important consequences for measuring the cosmic history of black hole formation and growth and studying the coevolution of black holes and galaxies. So there's ample motivation to study these black holes. So we observed Cygnus X1 in May, and then we had a second observation in June. That is for 300 kiloseconds, 242 kiloseconds. And this is like 6 days or so worth of data, and you see kind of that the flux was changing quite a lot. In the beginning, it's quite heavily absorbed. It's kind of when the black hole is behind the star. And then the Morse absorption is kind of, and then here we see some good flares. Overall, the source emitted at 1% of the Eddington luminosity, so that's the maximum luminosity you can get for higher the adding luminosity. For higher luminosities, radiation pressure on the electrons exceeds the gravitational pull on the ions. So this is kind of a just more or less typical luminosity for this black hole. And
does the Cygnus X1 pass in front of the star during that?
So there's no eclipse or so. And we think it's a 27-degree orbital inclination. So it kind of, there's some time where you have more matter from the wind.
Is one of those signatures going in front?
So basically here it's behind and here it's kind of in front. But it's not really behind it, it's kind of just at the far end and at the near end. This is kind of the phase, phase 0 where people get a lot of neutral hydrogen absorption. And this also comes out if we fit the X-ray energy spectra, that there's more matter here between us and the X-ray source. Right. So this just shows the energy spectrum. In the background, you see these are 3 detectors of this Imaging X-ray Polarization Explorer. And you see it's much higher signal than background. And on the right-hand side, you see in terms of the Stokes parameter, the results from the 3 telescopes, and the average result is this black data point. So overall, this is super far away from 0, and it's a super significant detection of the polarization. And this is the first highly significant detection ever of linear polarization from a black hole in the X-ray regime. Should I mention something else? Okay. So this shows the polarization as function of energy, and you see at low energies it's something like between 3 and 4% polarized, and then higher energies gets a bit bigger, and something seems to go to 6% or so. If you kind of look at it as function of energy, the polarization degree, it does increase significantly. We get like a 99.93% confidence level for an increase of polarization degree. This is like the flux dependence of the polarization. So the blue results polarization degree as function of energy. The blue is for the lowest flux and where the black hole is kind of behind the star. And the magenta one is when the black hole is kind of more on our side of the star. It seems that the polarization increases a bit. It's not highly significant, it's like 2.8 sigma or so. Right. So it may be increasing with the flux. Right. Okay. So this is kind of the most exciting result. This compares the polarization direction with that of the plasma outflow. So every black hole, some black holes show these jets of plasma coming out or coming from close to the black hole. It's probably related to the similar process if you have a little bucket of paint and you drop it and the paint shoots out. Some of the matter doesn't go into the black hole but comes out with high velocity. So this is like a picture where the side length is 10 billion kilometers taken with a very large array. And you see this gigantic radio jet, so it's a few billion kilometers. The X-rays that we see, we think they come from 35 Rg or so, from 35 gravitational radii. That's about 2,000 kilometers. And the black hole has a diameter of 60 kilometers. So this is a billion kilometer outflow, and now we can kind of see the X-ray polarization somehow tracks the symmetry of the X-ray bright region, which is only 2,000 kilometers. And we can see how this orientation compares to an orientation of the jet, 70 Rg diameter, sorry, 2,000 kilometer region. And you kind of, this graph, this yellow line and these regions show like the orientation of the X-ray polarization. So the X-ray polarization is, the electric field vector is parallel to the jet direction. And it's aligned to within 5 degrees or so. This 5-degree offset is not highly significant because different observers have seen get slightly different jet orientations. Maybe that's related to some radio absorption when the black hole goes around the star. So it's really nicely aligned. Polarization is parallel to the jet. We think this means that somehow the inner flow is perpendicular to the jet, and I'll show you that in a second. But it does kind of show that we don't have a scenario where the jet kind of bends a lot after leaving the central region. It seems to be still aligned with the innermost flow. So we combined this data with this Imaging X-ray Polarimetry Explorer with observation with other satellites, and that's the NISA satellite on the International Space Station, a NuSTAR hard X-ray telescope, an integral gamma ray telescope. And these observations kind of, you get the very detailed spectral shape over a broad energy range that can be used to constrain the contributions from different emission components. Also got some additional data from SWIFT and a Russian satellite. And this kind of shows like a multi-wavelength light curve. So on the top you get the IXPE flux variability with these flares at the later times. And NISA soft X-rays looks very similar. NuSTAR, we only had 3 days. But you kind of see some of the flares align if you kind of look through them. This is like at bit harder X-rays, and this is at much harder gamma rays almost, or hard X-rays. See, shows a bit that the flares align. So the source was variable at all energies. So this shows a broadband energy spectrum, and you see the different experiments, like NISA is the red points, and then the blue is NuSTAR, and the orange is integral. So this is the energy spectrum from a few keV to 250 keV almost. And you see there's some line emission. So if we fit that, there's some evidence for reflection of the inner portion of an accretion disk or so. It seems to be relativistically broadened. For the first time, we have not only intensity, but also Stokes parameter energy spectra. So that's the first in X-ray astronomy. And we modeled this then with different emission components, including like disk emission, thermal emission from the disk, a power law emission, reflected emission, and so here's its power law emission. This is reflected emission, and broad reflected emission and narrow reflected emission. Other way around, sorry. So the main result of this is that 90% of the flux seems to come from this power law, and so that the coronal emission dominates the X-ray emission in the X-ray band. And maybe the X-ray is mostly the polarization mostly tracks the polarization of this power law emission. But there may be a small contaminant by some other contributions. So the reflection contributes only 10%, the reflection of the disk. And so also did optical polarimetry. Let me not comment on this. So basically want to now interpret the results and see where this polarization comes from. Main idea is polarization may come from scattering. When X-rays, everything that scatters gets polarized perpendicular to the scattering plane. And that kind of can be understood with little dipoles not emitting in the direction pointing at you. So the scattering polarizes the X-rays. They could be polarized by the emission mechanism. For example, synchronous emission of electrons spiraling in the magnetic field can polarize the emission. Or general relativity also has an impact on the observed polarization. And that's because when the X-rays kind of go through curved space-time, the polarization stays perpendicular to the wave vector, and if the wave vector changes, it kind of turns around the polarization direction. So if you have some X-rays which go around the black hole, they are kind of differently polarized than X-rays which come straight at us. So it depends on the path, how the polarization is oriented. So overall, it changes polarization direction, but because, sorry, I shouldn't have, this is only direction. It doesn't change the degree if it just propagates. It changes then the polarization degree because you get X-rays from different regions, then some of them have a different polarization direction, and then it superimposes and gets a lower polarization degree. So we kind of were asking, where does this polarization from this black hole come from? And the first possibility you could think of is that it comes from X-rays reflecting off the star. if that would be true, you would kind of expect the polarization to turn around as the black hole orbits the star, seen at an orbital inclination of 27 degrees. So we don't see any time variability of the polarization direction, and this is therefore excluded. So this is excluded by the lack of orbital phase dependence. Then we thought maybe it comes from a distant source, like far away from the black hole, from the maybe created in the jet. This seems also to be excluded by the fact that we have a correlation of the flux and the polarization degree. Like we have, if the polarization would be produced by a contaminant from far away from the black hole, and then the flux from the black hole increases, the polarization should go down. But we observe that it goes up. So it seems that the polarization is produced close to the black hole and not far away from the black hole. So we think it tracks the X-ray emitting region. We looked at this different corona geometries. If you are an X-ray astronomer, you're probably familiar with these kind of lamppost models where there's a very compact light source above or below the black hole spin axis illuminating the accretion disk. So this is kind of this model, and it then illuminates, and this is the corona. We kind of also explored models in which the corona is some hot gas in the funnel region around the black hole spin axis, and the corona is around the thin accretion disk, or the corona replaces the inner part of the accretion disk. And all of these have different polarization signatures. I can briefly go through some of the models. For example, if we have like a central plasma, and we kind of assume it energizes photons to explain this very energetic X-rays by comptonization, then we would get kind of a lot of scattering along the axis of this plasma, would produce this perpendicular polarization. When the emission kind of comes from this and is reflected off the disk, you would kind of get a perpendicular polarization from here. And if it reflects off the front or the back of the disk, it would be horizontally polarized. And the polarization going around the black hole has yet another polarization, because the polarization kind of changes as the X-ray propagates around the black hole. So all of this, if you run the simulations, you see that you get very small polarization degrees for most inclinations. So if the inclination is the angle of the spin axis to, or the angular momentum axis of accretion disk to us, if the inclination is small, for example, you see it face on, or even at 60 degrees, we predict polarization degrees of smaller than 2%. And only if you go to very edge-on configuration, you see high polarization fractions. But if you see edge-on configuration, then this reflected emission dominates, and then the polarization becomes parallel to the disk. And it turns out it's parallel to the jet. So we think the polarization direction kind of argues against this outcome. So either the polarization fraction is small, or the direction is the wrong direction. So we kind of pretty much exclude all these lamppost models, where a lot of our colleagues are working on lamppost models. So it seems like that this primary emission that we see may not come from a lamppost. Should be careful, because maybe there are different models who can explain this. Just if you have like hot gas emits emission and it's like a spherical configuration, you usually predict very small polarization degrees, and it's difficult to produce something like 4% or 4 to 6%. While if you have a hot gas which has like a slab form, you predict higher polarization, because the electrons, you get a lot of photon scattering in this horizontal direction, and from that scattering you get a perpendicular polarization degree. So this one seems to, if the polarization comes from scattering in the hot gas, and this one is the preferred configuration. And this is like a model we ran for the sandwich geometry, where you have hot gas above and below the accretion disk. And you see kind of that you get at 2-3 keV, you get kind of to the 4 to 6% polarization degrees that you observe. And it's also slightly increasing with energy, which matches the predictions. And it is simulated to be perpendicular to the accretion disk in this case. This is like a model here on the right-hand side where you have the hot plasma being above and below the black hole on the spin axis. And then the polarization degree decreases with energy, and the angle is it has a 90-degree offset from what we expect it to be. So we think this is a kind of a more likely configuration. Then we also ran several extended lamppost corona where the corona is hot gas sitting above and below the black hole, but in a spherical shape. They tend to produce polarization degrees which decrease with energy, and they're usually not high enough. They're only high enough if you go to very low spins, which seems to contradict earlier measurements of the black hole spin. So we kind of exclude this also. Another model we ran is that the center of the disk is replaced by hot gas, and then the photons come from the side, from the accretion disk, into the hot portion of the accretion flow and get scattered. And that produces nicely high polarization degrees. If you go to inclinations like above 45 degrees, you can explain these 4 to 6% polarization degrees. Especially, so the left-hand side shows if the accretion disk just emits X-rays. The right-hand side shows if the photons which get energized in the hot gas are originally synchrotron photons. If these photons are synchrotron photons, then they have to scatter many, many times before they get to X-ray energies, and then the polarization degree is higher. So in the right-hand side, you have the synchrotron scenario, and this seems to explain the observed polarization degrees pretty well. Right. So this kind of puts everything together, and what you see on the is the polarization degree here, and it goes up as you go away from the center, and then also the polarization direction. And then here, the blue confidence regions are the IXPE polarization degree and direction confidence contours. So it's something like 4% polarized with pretty small error bars. And then you see, for example, that if you have lamppost coronas, they produce the wrong polarization direction, even though they can kind of explain similar polarization degrees. The same with this cone-shaped corona. Initially has a right polarization direction, but then it kind of gets off when the reflected emission starts to dominate. And then the only models which seem to work is that the corona is like a hot flow inside the accretion disk, or maybe synchrotron photons play a role in upscattered, or sandwiches the accretion disk. So these observations for the first time kind of constrain the geometry of this hot plasma. Should mention that if you try to image them, this black hole subtends like 10 to minus 15 degrees or so in the sky. So you cannot resolve it. You can only, this is the best geometrical information about the geometry of the accretion flow, because these objects are just too small. They're like many orders of magnitude smaller on the sky than M87 or Sagittarius A star, which you image in radio. It's also kind of interesting. Here you see the polarization of X-rays, where a lot of the energy really is produced, or most of the energy from the accretion flow. So you kind of get the accretion flow where it emits all of its power, rather than, yeah. So the overall geometry, we have like the 22 solar, the star, 41 solar masses, 22 solar radii. Very close to that, only 5 radii of the star away is the black hole. The orbital inclination is modeled to be 27 degrees. And then the jet is in the sky perpendicular to the accretion flow, the inner orientation of the accretion flow. And it seems also to be perpendicular to the orientation of the binary orbit. We get that from the optical polarization measurement. But then it seems, if we explain this as I showed you, by scattering in the hot flow, then we need to see the flow more edge-on than what we infer from optical observations. So if this is true, then we would kind of have some evidence for a misaligned black hole spin relative to the orbital angular momentum. Just call this Bardeen-Peterson effect. Some people also said maybe the inner accretion flow precesses, and we caught it when the accretion disk had a high inclination, was seen edge-on. But we exclude that by having repeated observations, and the repeated observations showed always the same polarization direction in degree. So there was no evidence for precession of the inner flow at these low timescales. It may precess very quickly on millisecond timescale or fraction of a second. So another worry was how much could the jet possibly contribute? And this is like a paper from 2020 where the hard state was modeled. And this is kind of the IXPE energy range. And this red stuff shows what we call Comptonized emission from hot electrons. They seem to dominate the emission. There may be some component from a jet. There's some spectral indication here at a few hundred keV and that the jet may contribute. But this jet only contributes about like 5 to 10% to the total flux. And so if the X-rays, if this here was X-ray emission from, if this was synchrotron emission from electrons in the jet, then to get the right polarization direction, we would have to assume that the magnetic field is bound around this plasma outflow or jet. And for this toroidal magnetic field, the maximum synchrotron polarization you get at 27-degree inclination is only 8%. So that if you dilute that and it only contributes 5% to the flux or 10%, you can only get up to 0.8%. And we observe 4 to 6%. So it seems that the jet alone, at least the synchrotron emission, cannot contribute enough, cannot explain the polarization. But there are some other explanations possible. Okay. So we hope if this is true, then the observation really constrain the shape of this hot gas, the geometry of the hot gas. Just to mention results to comparison to numerical results, some like Jason Dexter here make very detailed simulations of how black holes secrete plasma. And some of these simulations make predictions for the shape of the corona, the properties of corona, and then you could also make predictions about the polarization of the X-ray gas. So just to show here, to have a working plasma. So in these simulations by Kinch et al., these are depends a bit on the accretion luminosity, but you kind of see that you have some hot gas directly above and below the accretion disk, which looks a little bit like a sandwich configuration. But so these are kind of early results. They do it like simulation of the accretion disk and then post-process it and ray trace X-rays and see how the emitted energy spectrum would look like. So it's sometimes the same group should be able to predict polarization properties. Maybe a similar, interesting other result, numerical result, is from Matthew Liska et al. He kind of simulates magnetized accretion flows, and then in his latest simulations, he gets this kind of interesting result that in the inner portion of the accretion gas, the gas splits in cold clumps and hot clumps, and the hot ones could basically emit the X-rays, and the cold ones could reflect the X-rays. And so you get kind of a funny geometry, and haven't yet tried to simulate the polarization signal from that. Also showed some results from Jason here, where he simulated a hot accretion flow and then some X-ray bright regions, and he gets beautiful energy spectra, but still have to simulate the polarization of those X-rays. So that's kind of, I would say, in progress, and it's probably exciting for the next 10 years or so to compare the X-ray polarization measurements with detailed simulation results. So what is next? And IXPE has observed already 3 more black holes. And 4U1630 minus 47 is a black hole in the thermal state. So we have first thermal state results, where not the hot coronal gas emits most, but the accretion disk itself, we think. We observed Cygnus X3, which may be a neutron star, maybe a black hole, also in the hard state. And then right now, as we speak, we're observing LMC X1, which is always in the thermal state. So these results I cannot show you yet. Maybe only, so these will be upcoming soon. we hopefully will observe cygnus X1 soon also when it goes back into the thermal state. It went a little for a brief time into the thermal state where like the accretion disk is dominating and not the hot coronal gas. But then it was like just close to the sun and we couldn't look at it. So hopefully it will go into the thermal state again. Then we could measure the inclination of the system independently from these thermal state observations. And then we hope we can observe GS 1915 plus 105 as a famous black hole, but it has been a funny, very low flux, heavily absorbed state for a long time. So we haven't been looking at it yet. And we pushed it away from the observation plan until we see something, until it goes back into a brighter state. So maybe just to conclude, for that IXPE is sensitive enough to measure the linear polarization of 2 to 8 keV with high accuracy. It adds new information because you don't have only the intensity, but also the polarization fraction interaction. We can combine it with detailed simulations, numerical simulation, and expect really exciting results in the next 5 to 10 years into the inner workings of black holes. And then at the end, I'm kind of erasing this. Wanted to show you that there are a few other results. For example, we observed a few blazars. So these are supermassive black holes with jet pointing at the observer. And IXPE measured, for example, here the X-ray polarization of Markarian 501. That's a blazar that emits synchrotron X-rays. And the polarization is much higher than observed in the optical. This is at contemporaneous observations. It's like 10 to 12% instead of 4% in the optical. Probably means that the X-ray emitting electrons lose their energy faster radiatively, so that the X-ray emitting region just has a more homogeneous magnetic field than the optical, the field which is responsible for the optical emission. So maybe there's a shock that accelerates particles, and then the X-rays would kind of be emitted wide, very close to the shock, while the optical emission could come from further downstream where the magnetic field already kind of starts to tangle up or something. Or maybe it's reconnection and the X-rays come from a region where the magnetic field is more homogeneous. So that's one result for a blazar. Then we also have really exciting results from magnetars. That's the first one that was observed. And there was like a very significant detection already at 2 keV, and then it goes through a minimum almost zero polarization here, like at 4 keV, and then seemed to go to really high polarization fractions above 5 keV. So there's like a 90-degree swing. And if you're familiar with magnetar modeling, there are two modes in which X-rays can propagate, one parallel to the magnetic field, one perpendicular to the magnetic field. And it seemed that we see here the transition from one mode to the other mode. So this first observation was not yet good enough to show that, maybe you know that the vacuum also affects the polarization. And there's a prediction that if the quantum vacuum affects the polarization, that we could observe much higher polarization fractions. So that has not been seen for this first object, but the additional objects are being observed. And it's kind of exciting that you can probe quantum electrodynamics in a strong field regime with this. It's actually all I have for today. Thank you.
Questions? Yes, and preferably from the students and postdocs. Yeah.
So does misalignment between the black hole and the disk, can that save the lamppost in any way? Because of that?
Right.
Could you repeat the question?
So I think the question is, can you still save the lamppost in some way?
Yeah.
So I think we just talked with Mitch about possible interpretations. And one interpretation is that only a small flux is, for example, Compton scattered photons, Compton scattered by the jet. And if the jet maybe have some wide geometry, then maybe it can explain also the polarization direction. So if most what we see is X-rays from thermal comptonization, but a small fraction is produced differently with very high polarization degrees. Then you would kind of, this little contaminant would dominate the polarization. And that would then kind of, you could still kind of say that maybe the corona emission is not constrained by this, by our results. So in what we modeled, we can at least exclude that the synchrotron emission from the jet kind of contaminates the result, but maybe it's kind of a common emission from the jet. And then that would be like a savior for the lamppost model. But if what we see is really the comptonization from the corona, then it's kind of excluded. So it requires excessive fine-tuning. You have to have a lamppost corona moving away, to a disk with a truncation radius, and if you put everything together, then you may get to the high enough polarization degrees, but in what we modeled, it always went down with energy instead of going up. So we actually couldn't make it work for any lamppost scenario. So the only way would be some different explanation of the polarization we detect by some small contaminant. Favors the truncated disk over?
Yeah.
Over which one?
All lamppost or sandwich.
Right. So the sandwich seems good too. It's kind of interesting that the sandwich is very low polarized at 1 kV and rises, while the truncated disk is kind of high all the time. So at low energies, the truncated disk is a bit better, but overall, the sandwich is better because it describes a little bit of increased polarization. And the main effect is that, yeah. So I didn't let you ask a question, sorry.
So there is no, like, your data doesn't favor any of the models, like, only this?
So between these two models, they are both viable within the statistical accuracy. So to see this little effect here, the difference at low energy is kind of, it's at the limit of the statistical accuracy of the measurement. And we think by fine-tuning one or the other model, both could still be okay. There have been a lot of models of sandwich, which says the sandwich model actually emits a lot of photons which are reflected by the disk, and if those photons lose some energy, come back, then the sandwich, the reflected photons cool the corona too much, and you would overproduce soft photons. So maybe that there's that the sandwich would require basically some heating, maybe by reconnection or shocks or so, that you have in situ heating and you avoid this runaway cooling of the coronal gas for the sandwich model. That's like a model that independent observation that speaks against the sandwich model. But overall, sandwich and truncated disks seem to be consistent with the data.
The second one is in your source queue, I didn't see M87 or Sagittarius star because we have the resolved, at least radio images of that. So IXPE observations be correlated with the regularly resolved accretion disk images of that.
So for the phase, so your first question was does general relativity affect the phases of the waves as they propagate?
Not the phase of the wave. So if the plane of polarization rotates by a full 360,
right? Oh, that's true. Wait. So we could just, for that, so you say if you do rotate more than 360 degrees, how do we account for that? So all our models just have everything in them. And you get like some single scattering, you get multiple scattering, returning radiation. There's a lot of different contributions. And some of them may rotate more than once, but it's kind of accounted for more or less. But it's not that we can distinguish that. And for example, if you add or remove the reflection of the disk, that does make a difference. So the net polarization actually depends on a lot of individual ingredients. In this case, it's kind of good that the polarization is very strong. So for example, if you reflect, usually you reduce your overall polarization. And so this didn't worry us in this case, but disentangling the different contributions is pretty complicated. And then your second question?
The second one is, are you going to look at M87 or sideways stuff?
So overall, we can only look at the really brightest sources. So we need like sources which are like 50 milliquark, we say, more than 50, 0.045, the flux of the quark. So for AGNs and M87, it's really difficult for us. And so far, the AGNs we looked at, I actually have one more result here. For MCG or 523-16, we get a result which on 2 sigma levels consistent with 0. So for AGNs, this is actually, other than blazars, for AGNs and M87 and such a star, it's really difficult for us. This kind of, we get basically the brightest galactic objects which are good for this first generation polarization experiment.
Larry.
So what are the prospects for measuring the circular polarization Stokes parameter
Right.
B, and could that decide between some of the models that are still open from the linear polarization?
So I looked in this, it's a really interesting question, and looked at how you. So the question is, can you measure the circular polarization, and could that would that have power to distinguish between different models? So and overall in X-ray astronomy, it's all about detecting almost every photon because there are so few photons, and the polarization fraction you can constrain kind of scales with square root of number of photons, and so that's a real problem. If you want to measure circular polarization, there are a few methods. Some of them you scatter the photons off strongly magnetized iron foils, but the efficiency is like 10 to minus 6 or so. It's really low. So, and we need some efficiency close to 1. So we have like efficiencies here of 20 or 50% usually. So from a measurement perspective, that seems to be pretty impossible for the foreseeable future. There's some other methods where you take into account some properties of the atoms, but they usually only work over very narrow band passes. So both of these methods don't seem to have the accuracy or the throughput that you need to measure circular polarization. I have actually looked very, very little into the prediction for circular polarization. Usually it's also pretty low. But right now we always look at the linear polarization.
The two dominant circular polarization mechanisms favor low energy electrons or low energy photons. So it's kind of difficult to find a parameter space where it will be important for X-ray. Yeah. Go ahead.
I was wondering if we take the sandwich model for the corona, would there be a way to find the size of the corona or the angle above the horizon of the corona using polarization or any other method?
Right. So in this model that I did with these 70,000 different configurations, these parameters can be fitted.
Okay.
And when you fit them, you get kind of smallish error bars. But the bad thing is that this assumes a single temperature corona. In reality, it has a lot of temperatures. And it assumes a single stationary geometry, while in reality, we integrate over 300 kiloseconds, and the system changed on 1 second time scale. So overall, it's probably systematics limited. And the results you get on detailed coronal shapes may be you're kind of over-interpreting the data maybe. So we thought like this in the conclusion, if it's scattering, then the corona has to be perpendicular to the jet. This is kind of solid. But then going much beyond that may be kind of difficult. And the same happens to a lot of X-ray astronomy, that you have beautiful data with super small error bars. And when you fit, you get small error values. But it's all limited by systematics and the assumptions that go into these models.
Earlier on in your talk, you mentioned the spin of Cygnus X1, and it has previously been measured at 95% or more. Do your observations say anything about the spin?
So for this particular data set, they don't say anything, because you could have the spin mostly impacts like how close the accretion disk reaches to the black hole. And So we are fine even with low spins, can explain the data nicely, as well as the high spins. For future, we hope to see in the soft state, and then you kind of see like a transition from the perpendicular polarization to the disk, from X-rays returning to the disk, to the parallel polarization from X-rays far from the black hole. And then the energy at which the polarization swings by 90 degrees tells you something about the spin. So if we manage to see this 90-degree swing coming from far away polarization to the close polarization, then it would constrain the spin quite a lot.
Quite a lot, meaning as good as 95%?
Yeah, so that would be, for example, in the simulations where you assume everything is correct, you can kind of measure the spin to be 0.9 plus minus 0.02 or so. Independent just based on polarization, independent to continuous measurement or line measurement. So it will be interesting to look at the thermal state and see if it follows the predictions. And if it does, then we can kind of have a new method to measure the spin.
Okay. Tom, last question.
New star can observe the sun. It's actually done a series of very important measurements. Can IXPE observe the sun?
So, so the question is, can IXPE observe the sun? Which would be cool, because you see some solar flares and they could have Bremsstrahlung polarization. That would be really interesting. So the answer is no. I think it's mostly because of the thermal constraints. There is a sun avoidance angle. I don't know exactly if it's 30 degree or 40 degree, but we don't look close to the sun. With my balloon experiment, we did look into the sun. And so we also looked straight in the sun and would have been able to see a flare. And then we had a collaboration with solar physicists to alert us if there's a flare. But there was no flare while we observed. But we did look at the sun, and we were ready to, every day they told us which region may be flaring, and we were ready to go there. And the fluxes are so enormous, we could have gotten a really nice result. But
I mean, it seems to me that if you could observe the solar corona, coronal loops, for example, which are in some sense like your sandwich model,
right.
and maybe you can measure polarization in that particular circumstance, it might serve as a good calibration as well.
Right. So for IXPE, it's not possible. I think it's because of thermal constraints.
Have you observed the crab?
So, and the crab, so we, IXPE observed the crab. Yeah. So, well, I actually don't know if the results are public. So, probably, I think there may still be, whether or not I don't know. They may be embargoed, so I should probably not say. So they made phase resolved polarimetry. And there was polarization, a very narrow pulse around one of the two pulses.
Okay. Let's thank Henric once again.